Thank you, Sachin. You can kindly unshare. Okay. So the next session would be chaired by Suvrat. Suvrat, I have seen you. So yeah, okay. Over to you.
Okay, so thank you very much, 𝗦𝗶𝗶𝗶. Thank you very much also to the organizers. I was actually, I was on a break for the first few days, so I couldn't come, but I've been trying to catch as much of the conference on YouTube as possible. This is a discussion session on does the Hilbert space factorize in gravity, and the way I decided to organize it is I thought I would just speak for like, maybe 5 to 10 minutes to set the frame and define the questions, and then hopefully we can have 50 minutes of discussion. That is correct, right? We have 1 hour total, right?
Yes, Suvrat. Yes.
Okay, fine, thank you. Okay, so let me just set the frame, and we can hopefully have a lively discussion. I'll try and be as provocative as possible. Okay, great. So can you see this?
Yes, visible. Can you make it little?
Yes, I'll make it full screen. Yeah, thank you. Okay, great. So this is about, does the Hilbert space factorize in gravity? And let me try and define that question. I'll give you more specific questions. Let me just remind you first of all what we mean by Hilbert space factorization. Okay, usually, and it's something we just take for granted. It's so obvious. If you define a lattice field theory which has some set of qubits at every side, then if you look at this pink region here, and everything I'm saying is happening at one instant of time, and you look at this pink region here and you look at the yellow region, then there is a precise sense in which you can specify the state in the pink region entirely independently of the state in the yellow region. If you compare these two pictures, you'll see I flip this qubit from being up to down, this qubit from being up to down, but I could have done both of those operations or one of them or neither of them, and there's nothing that forces me to, relate those two. And that's the statement that the Hilbert space factorizes. Okay. Now, in gravity, in fact, I think in some sense we already know the answer to the question I framed, but I'll tell you what I think is interesting. We already know that in a sense, in a fine-grained sense, the Hilbert space does not factorize in this way. And the problem in gravity is much more severe than it is for gauge theories. And the precise statement one can make is that, the general slogan one can make it precise in various settings, is that if you have some qubits or some information that's present in the bulk of a Cauchy slice, then you can go to the boundary of the slice, and there is a sufficiently complicated set of correlators which allow you to read off what is happening in the middle of space. So you see, this is very different from factorization, and here is a picture to make that clear. In a non-gravitational theory, there's a sense in which you can define some excitation here and make things look exactly like the vacuum outside. You can change the excitation here and keep things looking like the vacuum outside. But in gravity, if you put an excitation, first you can't make things look like the vacuum outside some bounded region. There's some tail that goes out to infinity. What is more, if you change this excitation, you have to change the tails. So there's some one-to-one map, and clearly that tells you can't prepare the state of the bounded region independently of its complement. Okay, now why is this issue important? And let me point out, everything I'm talking about is about one bounded region and its complement. I'm not talking about situations where both regions extend to infinity. So this is important because it plays a key role in many issues and many questions of black hole information. And let me just point that out to tell you why the questions we are asking are interesting. So first of all, if you just go back to Hawking's argument and you ask, what was Hawking's key argument for information loss? So people often think in terms of, the calculation of Hawking radiation, but if you look at Hawking's paper, Hawking's, that was not really an argument, because even then Hawking knew that, small corrections could mimic mixed states, could make pure states look like mixed states. But really the argument that Hawking had was in terms of what he called the principle of ignorance, which was precisely the statement that you take a nice slice through the black hole space-time and the Hilbert space factorizes. So, he explicitly says in his paper, if you can see on your screen, let H2 be the Hilbert space of data on a hidden surface in the black hole, by which he meant the interior, H3 be the data outside, and then he introduced a factorization. He said, initial state goes to direct product of final states, and you have to trace over the interior. And so, if you don't have factorization, then this is a clear error in Hawking's argument. So people ask, where is the error in Hawking's argument? There is an error here in this assumption of factorization, which was very crucial to the argument. The same kind of assumption of factorization goes on, was used in the so-called monogamy paradox, which was set up by Mathur in 2009. And it was the same, you took a nice slice, and by means of a very nice argument, Mathur argued that, if you looked at the entanglement entropy of these regions A, B, and C, you could make some arguments that suggested it violated the monogamy of entanglement. But this entire argument assumed factorization, and it doesn't work if one doesn't have factorization. Okay, so far, these are things where people many people, I think, would now agree with what I said so far. But the interesting question I want to ask is that if you agree with me so far, then we have to follow this where it leads you. And let me point out, therefore, that in the argument that one gives for the page curve, usually, on which there's been a lot of recent attention, there is also an explicit assumption for factorization. In fact, if one goes and looks at Page's paper, this is Page's paper. This is explicitly what it says. It says, let the black hole subsystem be of dimension n, the radiation subsystem be of dimension m, and then these subsystems form a total system in a pure state. And if this argument, since I said in a very fine-grained sense, we know this argument is incorrect. So we also know that in a very fine-grained sense, if one looks at the von Neumann entropy on Scri+, it does not obey a Page curve, because there is once again this assumption of factorization. Okay, so that brings me to the question which I think is of interest, which is that there have recently been a large number of computations of the Page curve. The Page curve has been something very interesting. But in these models, the factorization that is necessary for the Page curve is achieved in some sense by force. And that is because, something that's not always discussed is that in these models, gravity behaves in a rather non-standard way. In particular, the way these models work is one takes some black hole in ADS and couples it to a non-gravitational path. And then one asks about information transfer across two parts of that path. And so I'll explain why that makes a difference to factorization. And secondly, even in the place where gravity is dynamical, the graviton has a mass, and that completely changes its information theoretic properties. Okay. So let me just say that thing again. As I said, you take a black hole in ADS, you couple it to a non-gravitational path, and the entire system has a description as a non-gravitational CFT on a theory with boundary called a BCFT. And then the computation that is done is you compute information transfer across some interface in this BCFT. So this is really like an ADS CMT computation, which is of interest because it's a question of computing entanglement between two parts of my lab which I have. But it's not very precise to term this the Page curve of Hawking radiation. And in fact, if you turn on gravity in the bath, then this Page curve goes away. Second, about the part where gravity is dynamical, as many of you know, there have already been talks in the conference. The tool that is used to do these computations is a so-called island proposal. But in a standard theory of gravity, where the Gauss law applies, the island proposal is just inconsistent in that it leads to a contradiction with the Gauss law, or it leads to a contradiction with the idea that you have an entanglement wedge. But these island proposals, these computations are all correct because in every case, the fact that you coupled ADS to a bath actually breaks diffeomorphism invariance and gives the graviton a mass. And so these are theories of massive gravity where the Hilbert space does factorize. Okay. So that being said, the questions that I think it would be very interesting to discuss for this session are the following. First, does the Hilbert space factorize at sufficient accuracy for standard theories of gravity in asymptotically flat space or small black holes, so that you can make sense of a radiation subsystem? Second, is there a natural, observable that follows the Page curve for black holes in asymptotically flat space? And then, is there a natural observable that follows the Page curve for small black holes in ADS? So these are the three questions I want to put forward for discussion. Before I open the floor, let me just explain these highlighted points about sufficient accuracy and natural. So first, I said Hilbert space factorizes for non-gravitational systems, but of course, we live in a world which has gravity, and so, we still say Hilbert space factorizes for qubits. And so, of course, if you coarse-grain a lot, you will get a Hilbert space that's factorized. So, if you wanted to observe the Page curve of coal, you would need to keep track of effects of size e to the minus s. But e to the minus s is still much larger than all of these unusual localization effects of gravity, which are controlled by g Newton times some energy scale to the d minus 2. So you ignore all Planck scale effects, you keep track of effects which are suppressed by the entropy of the system, and you will get factorization. For black holes, there's a subtlety because, and which we will discuss if there's discussion of small black holes. For black holes, this parameter that controls the unusual localization of black holes of information is 1 over the entropy. So if you need to keep track of effects of size e to the minus s, is there a sense in which you can ignore this unusual localization of information? Okay, that's the question. And secondly, I want to emphasize it would be nice to have a discussion of natural observables, because of course there is a sense in which one can just throw away gravitational effects and see a page curve. So in Scribe Plus actually is very precise, where we just throw away some components of the metric and keep others. Alternately, the equivalent procedures like considering the entropy from u to infinity instead of minus infinity to u. And there is a good chance that one might see a page curve subject to certain caveats. But it's a kind of an unnatural procedure. So there's no good justification for this except that, we wanted to see a page curve. These are the 3 questions that I had, which I think will be of interest to discuss. And as I said, I tried to explain what natural and sufficient accuracy was. So let me stop my lightning discussion here and throw this open to comments and whatever people want to say. I'll keep these questions up, but if someone wants to share the whiteboard, I can stop sharing.
Hi, Suvrat. Yeah, can I ask actually a basic question? So this is about, no, you can share your screen if you don't mind. The previous, the slide before the one on the massive gravity thing.
This one.
Yeah. So, this is just to clarify and to understand, since I haven't really followed very much of this. So when you say there's no Gauss law in massive gravity, so the constraints of general relativity are present. If you are breaking you're not really breaking diffeomorphism in an ultimate sense, you're maybe Higgsing it in some way. Wouldn't the constraints of general relativity still be present in any of these massive theories, or am I misunderstanding about?
Let me say in a more precise sense. So let me just write here. So usually, let's just look at the linearized theory. So usually the constraints. Can you see what I'm writing? Yeah. So usually the constraints in the linearized theory look like this, where on the right hand side you have the energy density. So if you integrate both sides, you find that this Ji is actually what turns into the ADM Hamiltonian. You find the integral of Ji at infinity is energy. So this is how one could derive the ADM Hamiltonian in the linearized theory. If you open Mr. Thornwheeler, this is how they'll first derive it, and then you say it's exact. In the presence of massive gravity, what you get is m squared times h. So now you see, there is nothing that gives you the total energy inside. So if you try to do the integral on both sides, you'll also get an integral of the metric. So there's a sense in which the constraint is not a total divergence. I can say this in another way. The way these so we don't understand massive gravity theories in all generality, but one way in which these theories are realized is by embedding a brane in ADS5. So one has these are the so-called doubly holographic models. So this is an ADS4 brane. And this is ADS5. You can take any other dimension, but I'll just take this. And this is the boundary. So what happens is you get this Randall-Sundram kind of localization of the graviton. So if you look at fluctuations of this ADS5, there's one mode which is a massive graviton mode that gets localized to this ADS4, and so this system has a different description as just gravity in ADS4 coupled to a bath. As I said here. So you can just get rid of the ADS5 and you have some gravity in ADS4 coupled to a bath. But you see here that it's obviously not the case that if you insert some energy here, that you can read it off just from here. You need to do an integral over this entire region. So in these setups, it's not the case that the Hamiltonian is a boundary term on the boundary of the brane. It's a boundary term in the higher dimensional ADS5. These are two ways to understand why the mass prevents, the Gauss law from acting. I don't have some more general statement about massive gravity in general, but this is a linearized statement, and this is a statement about one set of massive gravity theories that we know.
So, but there must be some sense in which, as you, I mean, the page curve. I mean, I am just a little worried about the discontinuity, so to say, when you consider with or without dynamical gravity. There must be some way in which you're saying that the factorization will be only an approximate factorization or something, and as you take the mass, let's say, going to zero, or what is the? I mean,
it's this point actually that so usually there's a sense in which you can make gravity weak. So you could have taken mass to zero, and you could have seen, you can make gravity weak, and you forget about these effects, and you still have approximate factorization. That's how we look at factorization in our world, right? We have 2 qubits here, 2 qubits here. The Hilbert space factorizes. In some sense, you could say, we are still living in a world with gravity. But of course, we work in a limit where you take gravity to be weak, you keep the entropy finite. For the case where you have the page curve, or where these computations have been done, as I said, the point of the discussion is to see if we can do something better. But in the case where there is no obvious sense, because the mass of the graviton is related to the Newton's constant on the brane, and that is 1 over the entropy. So in the limit where you try to take the mass to zero, the entropy also goes off to infinity. So it's so if you need to see the page curve, you need to keep track of observables of size e to the minus s, and there is no obvious way to keep track of those observables while while taking these gravitational effects to be weak, because these two parameters are linked together. For an ordinary system, they're not linked, and so there's a sense in which you forget about gravitational effects, you keep e to the minus effects, and you get factorization.
Sorry to go on, and others, I think, have also questions, but just I mean, this is, I can understand this about when Newton's constant is weak, but when you're kind of giving a mass to the graviton, isn't that slightly different? Is the parameter that governs this thing the same?
The same. At least in these W holographic models, it's the same thing. It's the brane angle that governs this mass. So, and this brane angle is also what governs the lower dimensional Newton's constant on the brane. So, at least in these models where these computations have been done, the Newton's constant and the mass, the lower dimension, the ratio of the lower dimensional Newton's constant to the 5-dimensional Newton's constant is controlled by this theta, and that also controls the mass. So in the limit where you try to take the mass to zero, you try and take theta to zero, the G Newton also goes off to zero. So indeed, it is the same parameter in this setup. Yeah.
Just to again a follow up on this. Is massive gravity the same as saying the stress tensor on the boundary is not conserved?
Yeah. Indeed. So that's the quickest way to see it. The fact that the stress tensor is not conserved. Therefore, the stress tensor picks up an anomalous dimension, because I mean, the conservation of the stress tensor in conformal representation theory is the statement that it's in a short representation. So if it's not conserved, it is in a long representation, and it has an anomalous dimension. But in the bulk, you can just do a one loop calculation. And if you have leaky boundary conditions, so Porati and Duff and so on did this many years ago. If you have leaky boundary conditions, it's like, it gives the graviton a mass through one loop effect in the bulk. But on the boundary, because the stress tensor is not conserved, it picks up an anomalous dimension. And then, by the standard rules of ADS-CFT, you would see that the bulk graviton would have a mass.
Just a couple of remarks, Suvrat. So first of all, I mean, maybe with respect to your second question here. So in asymptotically ADS spacetimes, the question is usually set up in the dual CFT, if you like, dual CFT description, if you like.
Yes.
Where where this factorization question makes complete sense, right? Now, I understand that in asymptotically flat spaces, perhaps more confusing, but to the extent that there is a holography for flat space, wouldn't you expect a similar like factorization to exist?
No, it doesn't make sense because you don't divide the CFT into subregions, right? When you do this, the black, if you could ask, of course, you could take just one part of the CFT and another part of the CFT, but if you look at a small black hole that's evaporating, there is no natural. So in fact, question 3 is, I think, the hardest question. If you just take a small black hole, this black hole is just sitting here, right? It's evaporating, and there's no natural region of the CFT one could associate with it. So you could do this plasma ball setup. Yeah, sorry. Yeah. Shiraz is on, but
sorry, what I meant was that, for example, in asymptotically ADS spaces, what you would do is you could always imagine like taking your dual CFT state and coupling it to a bath, right? Like there's a perfectly well-defined question where you say, I want to couple the CFT to a bath and then compute the entropy of the bath. Now, without any reference to gravity, I think that question makes sense, right? And so then why couldn't I do that for the putative quantum dual to flat space?
Because it's now not a standard theory of gravity. So if you couple it to a bath, you added a mass to the graviton. And what you're asking is a question about, so you have some CFT in your lab. So this bath is now not the black hole radiation. It's not like there's some one-to-one map. It's an ADS-CMT question. You have a bath and you're asking, what's the factorization of two paths? And it also so happens that the bath gives the graviton a mass through the back reaction, as we were discussing. So those are the computations which have been done. But those computations are computations of one part of the bath and another part of the bath. And the bath, in a theory of massive gravity in the bulk, where you use massive gravity as a tool to do that. So that's an interesting question. That's a question which is interesting in its own right. You can ask in n equal to 4, can I compute the entropy of one part of space with another part of space?
I think Omkar's question is, can you couple the dual of flat space theory to the bath? I think that would mean that somehow you're coupling the entire hologram of another system. That's what I understood from his question.
Okay. But first in ADS, if you couple it to a bath, you just change the theory. That's not. I mean, that's So we shouldn't say radiation. We should just say one part of bath and another part of bath, and that works. And also the theory becomes massive. But in flat space, you don't have to do that, right? Because black holes just evaporate. So why would you want to couple it to a bath? You could just ask.
That's the question he was phrasing. That's what I'm saying. But I think that both things will give rise to page curves. That's what I think. Because even if you have a finite cutoff, I think it will give you a page curve. So for example, there is one of the things that, let's imagine that what you're saying is, why would, for instance, subregions on screens behave like, the entanglement entropies or the RT surfaces that you define on them, the areas behave like they satisfy all the entanglement inequalities, even the obscure ones. So why do they do that?
One has to make this very precise. One can't just say, well, we just put some cutoff and then we compute something, right? So in ADS, it has been made precise.
I did not say that that's an entanglement. What I'm saying is that if you define a subregion on a screen, those subregions satisfy the properties of entanglement entropy, which is a different statement from saying that what entanglement entropy that is.
Maybe you should explain more. You mean that
if you it's in the Minkowski space. You take subregions on a screen, and you can compute RT surfaces, extremal surfaces anchored to that. That's just a geometric question, and they have areas, and these areas satisfy, like Araki, all kinds of inequalities, like strong subadditivity. In fact, we did this, but it's essentially in geometrically, this is a very trivial calculation, so we didn't write it up. But it's very straightforwardly follows. Even like monogamy of holographic entanglement, all of those things they just trivially follow. So I'm saying that the fact that those subregion areas have this property, it does not have an understanding in your picture.
Okay, yeah. Maybe the other people have their hands up, so they should say something. I think ICTS and Sandeep have their hands up.
Sure.
Please unmute yourselves and speak.
I think Ronak certainly before me. Yeah, ICTS, go ahead. And then Ronak.
So
in this slide where you compare the energy scales and the entropy of a black hole and so on, I understand the entropy comes from some microscopic counting in one way of looking at it. But like, if I really don't have a factorization, how do I even think of this entropy, like the naive black hole entropy?
Thanks. Yeah, I should have had a slide on that. So this is the thermodynamic entropy. So you would get it by an S maximization procedure. You do a set of coarse-grained, I mean, not saying we know how to compute it, but in principle, you do a set of coarse-grained observations, like very coarse-grained, like you compute like, a few low point correlators. And then you ask, what is the density matrix that gives you these answers, which has the maximum entropy? So it's the standard S maximization procedure. So a thermodynamic entropy makes sense with or without factorization. A von Neumann entropy is more delicate because it's a very fine-grained quantity. Just to say, the thermodynamic entropy makes sense for a pure state also, right? Whereas a von Neumann entropy can differentiate between a pure state and a mixed state. So all these questions, so thermodynamic entropy, there's no obstacle to defining, and you don't need factorization to define it. It's very easy to define for this reason.
I have to calculate coarse-grained entropy if I have access to everything on the space slice.
I couldn't hear.
If I do have access, I thought the coarse-grained is necessary because you have to make the correlations from outside. If you really have all the inside, do I still have to coarse-grain?
You could, right? I mean, I could say in this room, there's a sense I want to define an entropy for the room, even if it's in a pure state. I mean, that's in some sense the more meaningful thing to do. And there is a sense in which there's a degeneracy of microstates, which is related to the coarse-grained entropy. So that's a perfectly sensible question to ask. But it's not an entanglement entropy one is computing. I mean, the coarse-grained entropy, thermodynamic entropy is very important. Tells us the degeneracy of microstates. And it's easy to define with or without factorization.
Can I say something?
Yeah, Ronak and Sandeep and yeah. Please feel free also to just explode this thing and go wherever else you like. We can have a free-flowing discussion, but please go on.
Yeah. Ronak was before me. Ronak, go ahead, please.
Thanks. Actually, I was a rather simple technical question. So your statement that every excitation in the bulk of ADS needs a gravitational Wilson line to the boundary is the perturbative, as I understand it, is a perturbative version of the following statement, that every solution that differs in the bulk also differs at the boundary, right?
Yes.
Yeah. So, but then there are these bags of gold spacetimes which differ behind the horizon but not outside the horizon. How are these two facts consistent?
Okay, so So indeed, if you want to define holography, you have to exclude bags of gold, right? You have to say they're in a different superselection sector. If you want to define holography, it makes sense in the superselection sector that is obtained by asymptotic quantization. I think that's always true. You do asymptotic quantization starting from the boundary, and you look at all sets of states that you get, and then you bags of gold are not one of those. You could get other states which are not obtained by starting with a vacuum and exciting things from the vacuum, and those states, yeah. So I would suspect holography also doesn't work for those states, right? You can't know what's happening inside.
So there is a way in which holography can work, at least in the question of having too much entropy. People have suggested over the last 2 years that these bags of gold type spaces might just be non-orthogonal states in the boundary CFT.
Indeed, and then they would differ at the boundary, but there might be genuinely states which you can't see from the boundary. If there are states if there's just an e to the minus s inner product and you're overcounting, then there would be something you would see at the boundary that would differentiate between the states. So there would be certainly states of those kind which so Joydeep is going to give a talk, I think, tomorrow where he will describe this. You can just start exciting things in asymptotic quantization. You already look like you're overcounting the Hilbert space. And indeed, some e to the minus s resolves that. But there are also states where you just can't see what's happening and probably have to exclude them. Yeah.
Okay, thank you.
Sorry, Sandeep and Chetan, if you have another comment or your hand is just up from the start.
No, I think.
I think Sandeep and then Chetan. Yeah.
Okay. All right. I'll just ask the question. Then Suvrat, you can say you've told this to me many times, and then we can discuss it later. Others can. But just to ask you the question, okay? So I understand your arguments that if you take the asymptotically flat case and you keep all your operators, including your mu's or nu's or whatever, then you don't get a page curve. But now let me ask you the following question, sort of in terms of a physical set of experiments. Okay, let's say we have a set of observables very far away from the center where the black hole will form, spherically distributed, and they have little counters with which they can observe photons. And at time t equals to 0, a spherically symmetric shell of matter begins to collapse. They turn on their counters, say a little after that or whatever, or just around then. The matter collapses, forms a black hole and radiates. If they've started their counters at the time when, say, the collapse began, and after that they can, detect all the photons, what according to them will they measure? You say they won't measure the page curve. So what will they measure?
This is question number 2 on the screen. But if you just allow them to measure everything, including fluctuations of the metric, which they need to do to collect all information, like you just allow them to measure the metric and fluctuation, then they will just know at all times what the microstate is. But question number 2 is, is it somehow easier to see a page curve than it is to have all information?
Their detectors turn on at some time, though, Suvrat. Their detectors turn on at a time and they measure all physical excitations which hit their detectors.
Yeah, but the point is that you shouldn't think classically. So it's true that you're thinking the shell of matter past them, but the shell of matter passed them, but it left some imprints on the geometry which may have been very small. But remember that to see the information, these detectors need to be sensitive to e to the minus s degree of accuracy. If they're sensitive to that, they will be able to see the imprints that the shell of matter left as it collapsed. So they will just know at all times what went in.
Let's say they are arbitrarily accurate in terms of detecting gravitons and photons. But of course, since they start at time t equal to 0, that means they can't detect arbitrarily long wavelengths.
Yeah, I
That's
think
what I'm saying. It's a physical question. A black hole begins to form from collapse and I start off my detectors and I measure everything after that. I can't measure from the dawn of time.
Right.
So now what will I measure? Okay, sorry.
So can they measure the energy to good accuracy and correlators of the energy with other observables? Do they know how much energy is inside the space-time?
All the energy hitting their detectors, they will
but can they also measure the Riemann tensor so they can know how much energy is inside the space-time? And also fluctuations of that.
I don't know. We can continue later. You have to tell me. I mean, these are little harmonic oscillators which couple to the metric G mu nu, in their 2-state or something. We can model it. I don't know. You have to tell me what they can measure. I'm not.
If you allow them to measure the energy inside, in that, when they measure the metric, they can also determine from the Riemann tensor how much energy is inside, right? Because they can measure the deviation of geodesics. It's the way we measure the energy of the sun. So we don't actually go there, but we know how much. If they can do that, then and they have arbitrary accuracy in that, then they will know at all times what happened. But there might be a sense in which what you said is right, that somehow it is there's some observable which is more maybe this energy is somehow harder to measure. But if you just allow them to measure everything in the G mu nu to arbitrary accuracy, they will know at all times what happened.
It's the tails. I don't know. It's the tails which I thought you need to be able to measure down to t equal to minus infinity. I thought that's what worries me in your statement that you don't get a page curve. But maybe I'm wrong and others should continue.
Yes, yeah, indeed, that's a formal result, and maybe you're right. There's some physical obstruction there that somehow makes it easier for them to see the page curve. And maybe we can focus on 3. 3 is actually a question we can ask in the CFD, and I know I've discussed it with some people in the audience. Think of question 3. So think of just a small black hole that forms and evaporates in ADS. So on the boundary, you have like 2 blue balls that crash. They form some quark gluon plasma, and then they evaporate. And there's no spatial locality on the boundary. This is just happening all over the boundary. And now we want to ask, is there a natural set of observables that follows the page curve? And the counter argument the opposite point of view would be that the system doesn't unthermalize. You're trying to reconstruct the state of the initial glue balls, when there's a quark-gluon plasma, it looks like it's very hard because now there's a quark-gluon plasma. You wait for some more time, you again get blue balls. But it always becomes harder and harder by the second law to reconstruct the initial state. So it's not like it becomes easier or somehow it's easier to reconstruct the initial state. But maybe for some reason it's easier to determine the glue balls. Like the glue balls are easier. It's easier to make measurements in the glue ball phase than it is to make measurements in the quark-gluon plasma phase. And that's really the question here, which I think is an interesting question. I mean, is it?
Okay, yeah, let others ask.
Sorry, I'll stop.
No.
I think TIFR also has a question, and Chetan, so please, TIF, yeah.
Shall I go first?
Did you say TIFR?
Go ahead, Onkar.
Yes, because your hand is up at least.
Oh, okay. Yeah. So just a quick comment, or rather question about this massive graviton. Is it? Do you know what happens if at some late time we couple to a bath, and at some late time we decide to decouple the bath, right? So after that point, the stress tensor in the CFT dual to the black hole will be conserved, and at least in the future of that point in the black hole spacetime, we expect like a massless graviton, right? So
I don't think that will work.
So it's a question about whether that could be a potential.
It's an interesting story. So let's see what happens. So I'll try and annotate. So let's say you decouple here, like at this point. Okay, so this is your decoupling. So decoupling is like just changing the boundary conditions, right? So you can expect its effect to propagate causally in the bulk. So one way to model it is it sends a shock wave into the bulk, and it makes the graviton massless wherever the shock wave goes. So the graviton becomes massless in these red triangles. You see here? But the island is sitting here. It's a causal diamond here. I mean, as Shiraz and so on once pointed out very clearly, after decoupling, you should never be able to reach the island. That's a consistency condition. So indeed, these shock waves that set off at the time of decoupling can never reach the island. So the island is always in the region of massive gravity. This is a peculiarity of the black hole geometry. In empty ADS, if you wait for light crossing time of ADS, there's a transition time and the graviton becomes massless everywhere. But the black hole geometry looks like it does here. And so on a Cauchy slice, the graviton never becomes massless everywhere. It's massive in some regions of space and massless in some regions of space. And this is what happens if you try to decouple.
Thank you.
Can I go?
Yes, of course, please. Yeah. Sorry, yeah.
So,
actually, I don't know how to keep track of thing. Maybe Navamita can help me. Who's raised hands first?
I don't know that either.
Chetan and then Kaushik. Chetan, go ahead, please.
Hello, can you hear me?
Yeah, we can hear. Yeah, go ahead.
So, how do you understand ADS safety in this picture? Because I agree with what you said about this massive thing, decoupling. I never thought that it would work, but this shockwave type of thing. The island is always so much below. But I think that in order to get past, so let me ask you this question: how do you think about ADS safety? Because it is a bulk, localization type of thing, right? I mean, you're taking near horizon limit in the bulk. So how do you think of the usual derivation of ADS safety if there is no bulk radial factorization or something like that?
Yeah, that's a good question. I've thought about it a little bit. I guess there's a sense in which the decoupling limit must still work, right? One should think carefully about the order of limits one needs to take in the decoupling limit.
Only one limit, right? I mean, you're just taking a low energy limit and something. I mean, what do you mean?
Certainly, the effective field theory decouples, right? What you're asking is there a sense in which you can make it very precise? I think it's not clear the same obstacles arise, but do you have something more like sharper? Why you think
that? Like, see, it seems a priori the thing that you're doing when you're doing ADS CFT from flat space, if you have a bunch of brains or something, is that you're just localizing, zooming in on the black hole or the brain, right? I mean, that by necessity it requires you to have bulk factorization. How do you get past that? I never understood that.
But of course, one should never claim that factorization never works, right? That's the point of this, that would be an absurd claim. So clearly, there's a sense in which factorization does work
The
in some
objection that you said here about the entropy scaling is still there.
Is it? Why is it still there actually? Because
the black hole is entropy. I mean, you're the entropy of you're working with a D brane, right? I mean, black D brane.
Yeah, it's a near extremal D brane, of course. So these parameters are a little different. Yeah, in fact, I've thought about this at some point. Actually, it's not really, because it's not the case. I think this energy is much lower than it would be for this expression here. I think is not true for a near extremal brane. I think for a near extremal brane, GE to the D-2 can be much, at least for E, the Hawking radiation can be much smaller than 1 over SPH.
I would say that actually would work against you, because the point is that, for instance, in your, when you say Gauss law argument, for instance, when you want to have a Gauss law type of thing, the energy of the near horizon modes is actually, it's not detectable asymptotically, right? The modes
exactly.
that radius CFT are not detectable asymptotically.
No. So this is what makes factorization works better, right? This controls factorization, and it makes factorization means it works well, right?
Right. And so this is a situation with a black hole where factorization seems to work.
Indeed, it's in a near extremal geometric situation. Yeah. So it may be. Yeah, that's a good question actually, and I think Samir Mathur has also made this point. It may be that maybe for near extremal black holes, like if you're very close to extremality, there is a sense in which factorization works. So certainly in this case, these parameters you can decouple by giving the black hole a charge and by doing things, of course you don't see a page curve there. Yeah,
but I think that even at finite temperature black holes are far from extremality. I think the fact that the horizon has an infinite redshift is important. So if you are looking at a situation where there is an infinite redshift, then you're really, there is some sense in which you're going close to the zero energy, and that will always be difficult to detect from infinity. So, and I think that that's something that one has to worry about. Anyway, I think maybe I should let us.
Yeah, maybe that's true. Yeah. No, it might well be right. I mean, those gaps in energy are e to the minus s for a Schwarzschild black hole, but it might be right. You may be right that there's something which is there. You're right. Yeah, sorry. Kaushik had a point here.
Yeah, sorry, I'm trying to understand the question number 1.
Yes.
I don't mind being reprimanded as stupid. So, forget about gravity. Even in quantum field, take Klein-Gordon theory, scalar field theory. Even there, can I actually define something like a subsystem, like say a unit sphere at the origin and something outside? Do the Hilbert-Space factorize even there?
Yeah. Yes. There is an analog. It's not exactly factorization. It's called the split property. It's a statement.
So if I by factor, so that should be a kind of a tensor product, and that brings in all kinds of problems like this non-test class operator and all. Is that a problem or not?
So maybe now you're going into things which I don't understand. So somebody else should answer. Let me just tell you what I know. There is a split property in that you take some region R. You surround it with a complement which I'll call epsilon. This is some color, and then there's a complement which you call R bar. Then you can specify the state on R and R bar entirely independently, provided you have a small collar, which is this epsilon I drew. So it's not, things don't exactly factorize like they do in a lattice, but in a continuum theory, if you introduce a small collar, then including in gauge theories, by the way, even in a gauge theory, you can specify the state in R bar is specified entirely independently of the state in R. So in gauge theory, there are these obstacles. Yeah, sorry.
Right, but you will never be able to take epsilon to 0, right?
Yeah, you can never take epsilon to 0.
Yeah. Okay. Then I see. Okay. Yeah. Thank you.
Yeah. Sandeep and so on worked and Ronak and so on worked on this lack of factorization gauge theories. In the split property, you don't need to do any, you can always stuff enough charge in the collar. So you can't even make out the charge.
There's some theorem even in the standard infinite dimensional Hilbert space problems that the tensor products are not properly defined. I mean, the way we define it in terms of norms and all, there's a problem with the test class operators there.
Yeah, but would you be happy with the split property? I think that's enough. So I didn't say split property because it would have been too technical, but that's the precise.
Yeah, okay. Yeah, I understand now. Thank you. Yeah, thank you.
I think TIFR and if there's someone I'm forgetting, please just unmute yourself and speak. Ronak also has his hand up. So,
Hi. Yeah.
Oh.
Is anyone before me? No. Okay. So Surat, I actually wanted to. So there is this. Someone raised the point of the fact that soft operators are really hard to measure, right? And there was this paper that tried to get that tried to think about not defining regions on Scri+ per se, but defining regions slightly off Scri+ and being careful with diffeomorphism invariance. And they defined this thing called the effective entropy of the bulk effective theory. It was a paper by Zhaoliang, Qi, Zhi Dong, and others. And this, I think, is not in conflict with your results. So they find a page curve for this effective entropy. And I think it's not in conflict with your results because it very explicitly cannot include the soft operators, which you guys, which was so important for your work. Do you have any comments on this?
that was my understanding after a long discussion with Zhaoliang. But if you have more to say, indeed, that they in these tensor network models, one doesn't keep track of the constraints, is my understanding. So
yeah,
it's more,
exactly.
so yes. But if you have more to say, please go ahead and say it. I don't have more to say. Then I agree with that. Yeah.
So, yeah. So the okay. So perhaps one way to phrase it is one might think, okay, so the question of the page curve was imprecisely formulated earlier because of this ambiguity of the soft modes. Okay. And one position one might take, which is not necessarily my position, but I'm just describing something, is that the real question was the entropy of the radiation, not the entropy of Scri+. Yeah. So would you think this was a sufficiently natural question which gives a page curve and so on?
So yeah, I didn't see where they dealt with this issue of the fact that, sorry, maybe you should explain more if I'm missing something. I didn't see anywhere where they actually dealt with the subtlety that one has to deal with. So, radiation is defined as how, it's what Sandeep was saying earlier. If you have some set of detectors, they can measure the metric. And, so they can measure the metric fluctuations, whether those fluctuations are coming from fluctuations in energy or from something else, is not really a clean separation at very high accuracy. I mean, at a coarse grain level, it's a clean separation. Some photon comes and hits your detector. Yeah. But once you're measuring like fluctuations at very high accuracy, there's no clean separation. So so I'm not sure but that's maybe there is a clean separation which.
No, I don't think you need a clean separation to agree with their paper, because they would say that actually it's just all the effective theory degrees of freedom in a particular region, that region being defined in a diffeomorphism invariant way with Wilson lines and so on. And they would say, okay, some of that is radiation, some of that is just vacuum fluctuations, and that's fine. Like, that's not a problem for them.
But I think they would run into trouble already in perturbation theory. This is my understanding. Let's take the vacuum of ADS and look at the region outside the vacuum. So I asked them if they would say the entropy is. So let's just look at the region outside some large R in ADS.
Okay.
If I can measure the energy, I already know everything is in the vacuum. That's a Planck scale suppressed observable. Like, I have to measure the energy and know the energy is really zero. So I have to measure like some delicate fluctuations of the metric. That's enough to fix the full state in the bulk. This is at perturbative level already.
But this also requires. Sorry, go ahead.
Yeah, no. So at perturbative level, you already, if they define a non-zero entropy for the exterior of a ball, or for the interior of a ball, then we are already in trouble, right? If the moment you include perturbative gravity effects.
But again, I think it's important that they're not including the soft modes, right? So the analog of the boundary term in the ADM Hamiltonian is the soft mode in flat space, right?
Yes. So as Sandeep and Gautam and Shumit and so on define. So you throw out the Hamiltonian, right?
Yeah, basically you're throwing out the boundary Hamiltonian. Maybe you can think of it as a ring whose outer boundary doesn't exist, doesn't go all the way to asymptotic infinity. It's just a ring with two finite boundaries.
Yeah, but you go to the outer boundary and you measure some analog of the energy. You already get a lot of information about the inside. You could throw away the Hamiltonian, but it will reappear at next order in perturbation theory because it will appear in the OPE. So in ADS, it's very hard to throw away the Hamiltonian. So if you just ignore this and you say, well, we have a tensor network or some qubit model, then of course, you can define something. But if I think it's more subtle if you start keeping track of these effects.
I see. So they also had, apart from the tensor network, gravitational replica trick argument, right? Which maybe I didn't think about it in a very detailed manner, but it seemed to check all the boxes regarding the issues one might worry about. Do you think the gravitational argument there is wrong?
Sorry, yeah, we are discussing a paper which I have. My only impression has been in discussing this with the authors, in which my understanding is that this works when it throws away these constraints entirely. But maybe I'm misrepresenting, so please correct me. Anyone in the audience should correct me if I'm wrong. I think TIFR and so
a quick clarification on that. Just the question that he asked. I'll just ask, is that the paper where they're adding a cutoff in Euclidean, kind of like in the case of Gibbons-Hawking? That's the paper you're talking about? And computing the
no, this is the paper. Yeah, this is a paper where basically they define the boundary of a region in the exterior by attaching Wilson lines, and then they do a replica trick for this region. Okay, where basically the calculation is a calculation only of the entropy of the effective theory degrees of freedom, not of the gravity. Okay, so you have to be very careful, because now you're replicating the field theory but not the gravity at those points. And then they find islands for this replica trick, and they're very careful to make sure that when they do the replica trick, the replication back reacts, and so the precise position of the bulk region changes. And so for that they have to make sure that they're defining everything in a diff invariant way. So they deal with some of these issues with some care. I don't know if it's enough care. My understanding of this paper is still relatively coarse-grained. But so I thought this was the best argument for what it could be.
I think they start off from this Gibbons-Hawking cutoff. This is the impression I got when I think that's the point I was making. I agree with you that they're doing more than that, and they're doing it properly. They're actually doing a replica calculation. But I just wanted to make sure that we're talking about the same paper.
Okay.
Thank you.
Perhaps, yeah. Sorry. Thanks.
I think TIFR and then Somdatta.
Hi, Suvrat. Just going back to this question of whether the Hilbert space factorizes in quantum gravity. So suppose we just address it in just ordinary ADS CFT. N equals 4 Yang-Mills. Now, I suppose we expect that if we take just a flat spatial slice in the bulk, all of that is captured by the boundary at that time. And so it should be possible to do something on the boundary at that time to change something in the middle of the bulk, which of course is to create something, to create a particle in the middle of the bulk, which of course is in wild contradiction with factorization. Right. First, is this correct? And second, what kind of thing? It shouldn't be possible to do something too easy to do that, because this is in gross violation of semi-classical causality kind of intuition. I'm talking about changing, not measuring. Actually creating something then. So, what do you have some sense of what kind of thing we have to do? If this is correct, what kind of thing we have to do at the boundary to instantaneously change something in the bulk?
Yeah, indeed. That's correct, I think. And I think we can write down these operators. And as you say, changing is much harder than measuring. Measuring is much easier than changing. But we can write down some operators. These are these operators that look like it's some operator on the boundary times the projector on the vacuum times. You have to act with this operator. And to act with this operator is much harder than measuring this operator, because to measure the projector on the vacuum, you just measure the energy and see how much, whether it's 0 or not, or what's the probability of getting 0. But then here, these are some operators. These are local operators on the boundary. And this is some projector on the vacuum. But this operator you can approximate as e to the minus alpha h. So if you want to be very accurate, then you might think of this as a very high power of some metric. So you might think of this as some coordinated metric which acts all over the boundary, and you then raise that to a very high power to get an accurate projector on the vacuum. So at least to power log n.
Okay.
N is the ratio. Yeah.
Just as a follow-up, suppose we were allowing ourselves to use a band of time. Then we could write down the bulk operator, local operator in the middle, just using HKLM.
Absolutely.
Then we could try to we could try to take all those operators and back evolve them to t equals 0.
Yeah.
Now, is this when we discussed this in TIFR, it wasn't clear to us that this would give rise to some very complicated operation. But it felt like it should, because you shouldn't be able to too easily violate effective field theory, violate causality in such a crazy way. So is that related to what you're saying?
I think it will, right? Because you have to keep track of many commutators of the Hamiltonian. So if you act with this operator, and to really evolve, you're trying to squeeze an interval of ADS length down to some time, and you have to keep track of very high commutators of the Hamiltonian. So you try and expand in perturbation theory, you get H commutator operator, H commutator operator. So you'll get something which where you have to keep track of very high orders. So that's my best answer, but maybe there's a better answer. I think those are similar complexity things, but maybe that's not satisfactory. My best answer is that one has to just keep track of many commutators of the Hamiltonian in order to get something which acts deep inside the bulk, to get at least n commutators of the Hamiltonian. Otherwise, you're just doing something local. You're just trying to act with O plus O dot plus something. So if you keep track with n commutators of the Hamiltonian, then you start seeing this.
Yeah, sorry. One last thing, and I'll shut up. I'm sorry for taking so much time, but it's precisely this n that what it does. All you have to do is to back evolve in time of order pi, and there was no obvious n in that problem. For instance, when you try to take a simple operator and ask how long it takes to become a complicated operator under time evolution, that time scale has an n in it, some log n or something like that. Here we needed just a back evolve for a time of order pi. So it didn't seem clear to us that this was an enormously complicated thing to do in the sense of n scaling, but we probably got it wrong. So sorry, Eddie.
Yeah. You see, if you don't do any n scaling, then you're just trying to do a series expansion, right? It's like you're just trying to act with O plus O dot plus O double dot and trying to get O at a different time from that. And that usually would not work, right? I mean, there could be something which it would still be a local operation to all orders in dot, unless you did something. Isn't that so? Because every edge O gives you a one-time derivative. So it's like trying to act with O plus O dot, and you can't usually reconstruct an interval of length pi using that. But you're right, I'm not giving you the clearest answer, because I don't really have a clearer answer than the fact that at some point you should stop doing a series expansion if you think in those terms.
So, Suvrat, just
Yes.
to tell you,
Sorry,
we are at 5:40. So,
Okay, fine. Sorry. Yeah. Is there one? I think some people have been waiting. So Somadat has been waiting. Can we just have him speak, and then we can stop? I'll stop sharing. Yes.
Yeah. So I was just thinking about, like, if you have a pure state. Okay. So if you have a pure state gravitating in order to form a black hole, a pure state in configuration space, in field configuration space, is a linear superposition of delta functions in configuration space, right? Is that correct?
I didn't understand why. Yeah, linear function of delta functions in yeah, sure.
Linear superpositions of delta functions in configuration space, just like a wave function in ordinary space is a linear superposition of delta functions in ordinary space.
Okay.
So now, when it tries to gravitate, what it means is that it has to scatter off some graviton, right? Now, when a pure state scatters off some graviton, it automatically collapses to one of these delta functions, right?
Yeah, I'm not sure, but maybe you should complete. Yeah, please complete what you're saying.
So in order to gravitate, it has to scatter off gravitons, and once it scatters off gravitons, it collapses to one of these configuration space states, and then it loses all its information, because once a state collapses to one of its delta functions, it loses all its information. So I don't see how information loss, so information is lost in the very first instance when it starts to gravitate. That's all I'm saying.
Yeah, maybe we can also just get ICTS to say something. They have their hand up. I'm sorry, I didn't notice it right now. We just finished running out of time, so please, yeah.
Am I audible? Hello, am I audible?
Yes, please. Yes.
So would you also this objection to coupling anything to the boundary theory? Would you also say I shouldn't be really using the generating functional dictionary in holography?
With the source turned on, like a finite source turned on, you always look at derivatives of the generating function.
So for any ordinary theory, like you could calculate put in a and then like at a second step, like, lift it to something dynamical to like think of the theory coupling to something else. But now it seems to be that you are saying like the moment you couple anything to say n equal to 4, it seems to be drastically changing the theory, right? Because now
in the bulk, I mean, the stress tensor is not conserved. So I mean, something which was earlier a conserved quantity is now not conserved. It picks up an anomalous dimension. That's all that's happening.
And then when the statement is there's a drastic discontinuity when you turn off the coupling, anything exterior, right? There's no continuous limit in which you can think of something to the n equal to 4, and then you turn off the coupling because the bulk, there's a discontinuity from the bulk being massive to massless.
Yeah, that's what we discussed sometime back. You know, yeah, you can turn it off and then you get some picture in the bulk where the graviton is massless in some regions of space and massive in some regions.
I'm getting confused in this way, like is it meaningful to couple anything to n equal to 4 or not?
You can couple something to n equal to 4, sure. You'll just get a stress tensor which is not conserved. Maybe Chetan has something to say and we can discuss, Akhil, because I think we are totally out of time. Sorry, Navamitra said me out.
Sorry,
Okay.
I'm sorry. I'm really sorry. Actually, Lara is waiting for last 10 minutes. So Suvrat, you are muted.
Thank you. I was shutting up, so I was muted. Thank you.
I'm really sorry.
Thank you.
Ask you to stop.
Yeah.
Okay.